Welcome to part 3 of this week's online lecture. In part 3 we will discuss analysis by infrared techniques. But before analysing a sample we need to prepare it for analysis, and the preparation will depend on whether the sample is a liquid, solid or gas. The next few slides in this section will illustrate how this can be done. Liquid samples can be sealed in a liquid cell assembly. The liquid is placed in this sealed assembly here. Solid samples can be ground together with potassium bromide. Remember that potassium bromide is transparent in the infrared, but you must use spectrophotometric grade potassium bromide. The sample can then be cast as a potassium bromide disc in a hydraulic press. But as potassium bromide is hygroscopic, this must all be done under dry conditions. Indeed, during the pressing you need to evacuate the assembly. About 8 to 10 tons of pressure for some 3 to 5 minutes are required to form the potassium bromide disc. This slide shows the die assembly prior to being placed in the hydraulic press. Alternatively, rather than grinding your sample together with the potassium bromide, you can use Nugel, which is a liquid paraffin with few infrared spectral features to make a mull. The spectral features of Nugel can be seen in this spectrum. It is important, therefore, that the spectral features of your sample do not overlap significantly with the Nugel. Gas samples can be placed in gas cells, which you may have used already for the HCl experiment in CM2101. As molecules in gases are much further apart than in solids or liquids, it is important to use a longer path length, and this explains the length of this gas cell. This path length could be increased further by using mirrors so that the source radiation passes through the cell many times before reaching the detector. If we look at the spectrum of methyl iodide in the gas phase, we can see that the bands are often resolved into the rotational fine structure. However, if we look at the spectrum of methyl iodide in the liquid phase, we can no longer resolve the rotational structure. This is because collisions leads to essentially random changing in orientation, known as tumbling, and this leads to very short lifetimes of the rotational states, which in turn blurs the rotational structure in the vibrational spectrum. In the solid phase, molecules are unable to rotate freely, and the vibrational band appears as a single envelope of rotational lines. This is the end of part 3 of this week's online lecture. Please continue on to part 4.